So thank you for attending this morning lecture. This is the second session, scientific session at NASCI, and we'll be having 3 presenters.
Okay. The first one is Amin Mahmoudi. He's a MD PhD student at UC San Diego, working with Dr. Sao to apply deep learning techniques to advance cardiac MRI. And he's going to be presenting on deep learning analysis of cardiac volumetry and function with real-time MRI. The floor is yours.
Thanks so much. Pleasure. Okay, please let me know when to begin.
Oh, yes, sure. It's
Okay.
yours.
All right, so hello everybody. We'll be presenting on deep learning analysis of cardiac volume and function as was mentioned, and our acknowledgements are that we have research support from GE Healthcare as well as Dr. Chow has intellectual property rights at Arteris. So let's begin by what was the motivation for this study? It's no surprise to everyone in this crowd that heart disease is the leading cause of death in the United States and also globally. And cardiac MRI can be used to identify and diagnose a number of different etiologies of cardiovascular disease. In the specific study, they found that it was up to 55% definitively diagnostic and an additional 25% of incremental diagnostic value. And even when other diagnostic workups such as echocardiography was performed, it helped to change the management of that patient up to 40% of the time. So that begs to ask the question, what is the standard of care for cardiac MRI? That would be the breath-held EKG-gated cine, where the patient holds a breath for up to 10 seconds or more, and then an EKG compatible with the MRI is used to trigger the MRI acquisition. How that works exactly is that the R peak of the EKG is used to trigger a multi-phase acquisition, where multiple different cardiac phases throughout the cardiac cycle are partially filled in their spatial frequency maps. Then subsequent cardiac cycles are used to complete each of these spatial frequency maps based on the phase of the cardiac cycle. Through mathematical interpretation, here's the inverse Fourier equation, those spatial frequency maps can be turned into MR images. What's the problem with this? Well, the limitation of EKG gating is that there can be physiological discrepancies to the RR interval. Here in atrial fibrillation is shown and how that disrupts that image. Also, there can be technical disruptions to the EKG signal, such as R peak attenuation through magnetic field interferences at increasing magnetic field, and here's how that distorts the image. Well, what are the solutions? We heard 2 throughout this conference, and one was to fix the EKG gating, 2 was to increase the speed at which we reconstruct that image. Well, another solution I'm proposing here is to use an MRI modality that does not depend on EKG gating and is free breathing, such as a real-time MRI. Its difference would be that each image is acquired in a single acquisition, single phase fashion, where the entire case space or the spatial frequency map is constructed and the image is constructed. So the subsequent cardiac cycles do not affect the previous images, and each image is independent on its own. What's the problem here? Well, because it's EKG free, we don't have the information about the phase of the cardiac cycle. So the identification of where in the cardiac cycle each of these images are done by hand by either a cardiologist or a radiologist, which is time and labor intensive. So why don't we just use deep learning to pick these images out and figure out what phase of the cardiac cycle we're in. Here we can see 3 slices of a real-time data set from one patient, and we can use deep learning to figure out exactly where, for example, the end diastolic phase is. And when we know where that phase is, well, we can then create a stack using that phase, and that stack can then create a volume, which will then be enabling automatic measurement of functions such as ejection fraction, as well as other global metrics. How do we go ahead and do this? Well, as mentioned, we use deep learning to identify end diastole and end systolic phase from real-time MRI. We also employed deep learning to figure out where in the ventricular slices they are so we can isolate the ventricle, and we stitch these together based on the end diastolic intervals to create the pseudo-cine volumes. And specifically, I'll be detailing how we use cine data to train a deep learning network to be able to predict on real-time data. And that took a number of steps, which I'll detail. We had 241 patients with short axis cine SSFP images. Each of these patients had 20 cardiac slices, frames, with temporal steps of 37 milliseconds. Each of them had the end diastolic and end systolic phase available courtesy of the EKG gating. And what we did was we downsampled this spatially to mimic a real-time acquisition that has lower spatial resolution. How we did that was through manipulation of the spatial frequency map, as detailed in the literature, which I won't talk about here. Then we took these spatially downsampled information and we grabbed each of the adjacent frames and temporally interpolated 10 times between them to temporally downsample. And subsampling from these many frames at different temporal steps allowed us to have variations in the time between each of the frames. In order to see where each frame that we have created is in comparison to end diastole, we convolved it with we convolved the end diastole label with a Gaussian convolution, so we can distribute that temporal information across all of these frames and understand how close they are each to end diastole or end systole. Now that we have this information, we used it to train a deep learning network that would take the successive images of real time, or in this case, synthetic real time as input, and output 2 channels of essentially probability estimates of how likely are each of these images to be either end diastole in one channel or end systole in another channel. Comparing these to the test set in the actual synthetic real-time data that we had created, we see that we were very highly accurately able to predict the end diastole at the frame that it was labeled using the EKG, and also even more accurately if we were to give it 1 frame leniency to the before or after. And we also had very high recall, which is another word for sensitivity. And when we were testing this in 11 patients who had actual real-time data, we saw that recall was near perfect, both had 0 and 1 frame leniency, so there were no false negatives. However, we took a hit to the accuracy, which means there were some false positives being determined by our model. Here's what that would look like in 1 patient, for example. We have 3 slices of a real-time data. Each slice has multiple frames, and these frames were labeled by 2 physician scientists in training and overseen by 2 cardiothoracic radiologists for both end diastole and end systole. Further, that was correlated with the EKG signal for each of those patients. Our model predicts very accurately where end diastole and end systole is for each of these slices, as shown. So then we can use this information to create these stacks, as was mentioned earlier. And if we were to compare these volume stacks that were created from the pseudocinae to the actual cinae from these 11 patients, we see strong positive correlation between both the real-time created images, volumes, as well as the cine volumes. Furthermore, per patient breakdown shows us that there is a general underestimation of the end diastolic volume and overestimation of the end systolic volume per patient in the pseudocinae, and that makes sense since the real-time data has a lower temporal resolution, and you're not always necessarily grabbing, for example, the exact end diastolic frame or the exact end systolic frame. So in conclusion, we see that deep learning algorithm can be capable of differentiating the cardiac phase from a real-time SSFE image, and that can enable cardiac volumetry, which will be comparable to the cine as shown. And this may enable a more reliable MRI and measure of cardiac function for patients that are unable to tolerate cine acquisition techniques, so they can't breath hold or they have arrhythmias. I'd like to acknowledge everyone at the UCSC IDA lab, specifically my co-authors noted here. Thank you.
Any questions from the floor? Okay, actually, I have a question for you. So just more of a technical question. So what are the challenges you're facing to be able to implement such a robust AI protocol in terms of computational powers of the computers in the workflow? So I'm trying to see how this is easily applicable in our clinical workstations.
Yeah, so the main application of this protocol is a post-processing technique. So one of the bigger challenges is kind of prior to this even being implemented, and that's to increase the temporal resolution and spatial resolution of real-time acquisition techniques, which there are a number of different techniques coming out, parallel imaging, accelerated imaging, that are pushing that frontier, as we heard during the GE breakfast talk as well. This would be after the fact, so the computational burden would not necessarily hinder the acquisition process of the MRI. I'm not sure if that answered your question.
Yeah, thank you.
Thank you.
Good presentation.
Thank you very much.